For decades, rendering a virtual environment meant building it out of triangle meshes. These are essentially rigid, hollow shells. They are computationally cheap, but because they only represent a surface, making them look perfectly real is incredibly difficult. The traditional workaround is a technique called structure from motion. It works by analyzing photographs and tracking specific points across multiple angles to build a sparse 3D map. But it has a fatal blind spot. If you point it at a flat, textureless surface like a blank white wall, it loses track of the points and the geometry collapses. 3D Gaussian splatting solves this geometry problem. Instead of plotting a hollow surface, it drops millions of individual points into a space and expands them into semi-transparent, mathematically defined ellipsoids. This comparison shows the visual result. The Gaussian splatting model on the right constructs the bulldozer and the bonsai tree by mapping light, color, and opacity to every individual ellipsoid. It skips the heavy processing required by neural networks, rendering highly accurate details at 90 frames per second. By achieving this fidelity 10 times faster than previous methods, 3DGS removes the computational wall that kept photorealistic 3D models locked in high-end labs. It makes the mass production of high-fidelity virtual space economically viable for the first time. Early versions of Gaussian splatting still relied on those flawed point clouds to figure out where to place the ellipsoids in the first place. When the system encountered those blank walls, it generated broken geometry and floating artifacts. The fix requires dropping the point clouds entirely. Instead, engineers use monocular depth estimation, analyzing a flat image to generate an explicit depth map. This creates a trade-off. The old method mapped true physical scale, but left holes. The new depth map sees smooth walls perfectly, but loses the true scale. This distortion is a problem known as scale ambiguity. This technical breakdown shows how researchers mathematically align these conflicting systems. By applying a specific transformation algorithm, they force the smooth depth map to shift and align perfectly with the true scale of the room, fixing the architectural lines you see in the highlighted boxes. With the scale locked in and the floating artifacts deleted, developers can render massive kilometer-scale environments instantly. The Phygital world, a seamless blend of physical environments and digital interactions, is shifting from a futuristic concept to a measurable market. This transition is being driven by a strategic move away from raw hardware power toward algorithmic efficiency. Rendering complex 3D environments normally requires massive computing clusters, which makes U.S. export bans on high-end semiconductors highly restrictive. However, Gaussian splatting's rasterization process is lightweight enough to run beautifully on consumer-grade chips. That algorithm efficiency frees up computational headroom. Companies like ByteDance are taking that extra power and aiming it squarely at the hardest problem in AI video generation, keeping spatial geometry and character identities consistent across camera movements. ByteDance's CDance 2.0 tackles this by taking text, image, audio, and video inputs simultaneously. It uses this multimodal data to build an implicit understanding of a three-dimensional space, forcing the generated pixels to obey strict physical laws like gravity and realistic shadowing. Owning the models that successfully enforce physical consistency provides a clear advantage in the race to control next-generation spatial media. Software code only covers half the strategy. To build a dominant ecosystem, these companies are constructing the physical devices required to view this content. Tencent is releasing Hunyuan, a movie-grade spatial video generation model designed specifically to integrate into industrial commercial applications. ByteDance has integrated Gaussian splatting directly into the Pico 4 Ultra headset. The device renders the math natively, enabling a user to walk through a volumetric memory as if you were physically present in the original space. By pairing the algorithms that generate the environment with the hardware required to explore it, these companies lock developers and users into a completely sovereign pipeline. This flowchart maps the 3D Gaussian ecosystem. To ensure there is a constant supply of engineers building within this architecture, these corporations standardize their workflows by sponsoring massive academic competitions. The SIGGRAPH Asia 2025 workshop, sponsored by Huawei and Zhejiang University, acts as a global recruiting ground. Competitors have exactly 60 seconds to reconstruct a complete 3D scene, measured by peak signal-to-noise ratio. They must parse 3 rigid files, a video, camera parameters, and pose matrices, then integrate point cloud data and map frames to microsecond timestamps. Training the world's engineering talent to master these specific file formats ensures the global workforce is building for a proprietary architecture. To even land on the leaderboard, a team must output the exact calculated signal ratio, a properly formatted point cloud file, and the synthesized views. Packaging protocols are rigid. Submissions require a technical summary compressed into a results zip file, with a mandatory 3DGS prefix attached to the team name. Deviating from that naming convention results in immediate disqualification. When thousands of engineers adopt these specific formatting rules and evaluation metrics, they embed these technical standards into the foundational layer of their professional workflow. Every downloaded dataset and optimized script solidifies a global dependency on these tools. The physical and digital worlds are merging, and the infrastructure holding them together is built, regulated, and owned by a China-led hegemony.